I'm Michael Coblenz, and today I'd like to talk about evaluating programming languages. A programming language I view in this work as a user interface that people can use to accomplish various programming goals. So the question is whether we can evaluate whether a particular programming language design is better than some other language design. And of course, we'll need to do this in some context. We'll have some users and some tasks. And this is especially challenging if the language is very novel, so we'll need to teach our users our new programming language as part of our evaluation process. There's some existing work on this. For example, Honenberg compared static and dynamic types, and Usbeck and others worked on C++ lambdas. In this work, I'm going to focus on unfamiliar, strongly typed languages that provide strong safety guarantees. And what we found is that indeed we were able to evaluate these languages in experiments and compare them to existing languages. So I'd like to talk a little bit about what we did and how we did it. The context for this work is that of user-centered programming language design. That is, we want to not only design a language and show that it's better, hopefully, than some existing language, but also integrate user input into the entire design process. In this talk, though, I'm going to focus on the evaluation step, in which we do a comparative analysis of our new language with some other language. The context is of blockchains and smart contracts. Blockchains, as you might know, are distributed ledgers that can be used by parties that haven't established trust. Smart contracts are a term for programs that run on these platforms. Some examples include things like bonds and insurance applications, gambling, or supply chain kinds of applications. Unfortunately, a lot of these programs have been exploited by hackers to the tune of millions of dollars. So the idea is that we want to design a safer programming language in order to prevent some of these bugs. So we designed a new programming language called Obsidian, which stands for Overhauling Blockchains with States to Improve Development of Interactive Application Notation. And we based our design on two observations about blockchain applications. One is that blockchain applications frequently support different operations depending on the state the objects are in. You can think of the DAO hack as relating to this class of bugs, in which people accidentally invoked operations on an object when it was in an inappropriate state. And then also, a lot of blockchain applications manage important assets like virtual currencies. And some of the bugs that we've seen, at least in laboratory studies, have involved trapped or forgotten assets. So we're going to use two approaches from type systems in order to address these bugs and integrate them into Obsidian in order to obtain better safety guarantees. So we have this notion of Typestate and linearity, which I'm going to introduce in just a moment. But this combination is new in a programming language, and neither technique has been shown to be usable even in isolation. So without Typestate, in the context of, say, Java, for example, the type doesn't have any state information. So here we have this light switch object x, and the reference x can point to a light switch in any state. We don't know statically which state the object is in. On the other hand, by adding state to our types, we can specify that x is specifically a reference to an object that is known statically to be an off state. Likewise, without linearity, suppose we have a reference m to some money, and we have a transfer money operation that can send that money to somebody. We can transfer the money to Alice, and then we can transfer it to Bob, and the compiler is fine with that, even though this should give some sort of runtime error, because of course once the money's been transferred to Alice, we can't also transfer it to Bob. However, with linearity, we can capture a notion of ownership in the type system. So here, m is initially owned, and when we transfer m to Alice, the type of m actually changes from owned money to unowned money. And then the second invocation of transfer money will fail to type check because m is not an appropriate type for transfer money because m is unowned at this point, whereas transfer money requires an owned argument. This allows the compiler to give an error message rather than waiting until runtime to discover the bug. Now, it's tricky because of aliasing. So here's an example where we have two different references to the same light switch object. Initially, the object is in state off, which is fine, but then suppose we use the reference on the left to turn the state of the switch on. So now, from this perspective of the reference on the right, we have a problem because the static type is off, but in fact the switch is dynamically on. So this would be unsound if we allowed this, so we can't allow this kind of a situation. So one rule we have is that if there is any type state specifying reference, then all other references can't change type state. So I want to walk you through an example of some Obsidian code. Here we have an insurance policy, and you'll see there are these three states that an insurance policy is in. Initially it's active, and then eventually it may be either claimed or expired, as somebody either files a claim or nobody ever files a claim, and the money gets returned to the company that issued the insurance. So you see, when we're in active state, we hold money, which we call benefit here. So the idea is that maybe we don't trust the insurer to actually pay out when an insurance claim is filed. So the insurance policy itself holds the money. So when the state is active, the money is waiting around for something to happen. But when the state changes to claimed or expired, there's no money anymore because the money has been transferred somewhere else. So here we're looking at the constructor. When we construct an insurance policy object, it's going to be an active state when the constructor exits. The constructor takes an argument M, which is initially of type money at owned, meaning the caller must pass an owned reference. But afterwards, we guarantee to take ownership of the argument. So afterward, from the perspective of the caller, M is unowned. So what does the body do? Well, in the body, we transition to active state, and we initialize the benefit field with M. So this assignment here transfers ownership from the parameter M to the benefit field. Now let's look at the claim transaction. The claim transaction can only be invoked on an insurance policy that is known to be in active state. And you can see there's a special this parameter on the claim transaction indicating that fact. In addition, we promise that after the claim transaction finishes, the state of the insurance policy will transition to claimed. That's the meaning of the double arrow there. And finally, it returns money to the caller. This is going to be the payout of the insurance policy. So let's step through how this works. First, we assign from the benefit field to a temporary variable result. Then we transition to claimed state. Now the compiler checks to make sure that all fields that could own assets do not anymore. And indeed, we've transferred ownership from benefit to result. So this is okay. So we transition to claimed state, which does not have the benefit field. And then we return result to the caller. Now, given this language, we wanted to know whether we could show that it was better than Solidity, or in fact, whether it was the case. So the first question is whether we would be able to conduct a user study in an unfamiliar language at all. Maybe we'd have to have too much trouble recruiting and training participants in this unfamiliar language. But if we could do that, then we were interested in finding out whether people were able to complete tasks in Obsidian despite the complex type system, right? You could imagine maybe the type system could be so complicated that people couldn't get their work done. And then finally, whether Solidity users would insert the kinds of bugs that Obsidian detects, right? Because otherwise it's not worth going to a lot of trouble to detect and prevent those kinds of bugs. So we recruited 20 participants. They had a median of 6 years of programming experience, a year of professional experience, and 2 years of Java experience. We think this is reflective of at least some fraction of professional software engineers. There was a Stack Overflow survey that found that 41% of practicing software engineers have less than 5 years of experience. So our participants may reflect that kind of developer population. So in the experiment, we gave people a tutorial on their assigned condition. We gave them practice problems and a compiler, and they had someone available who could answer their questions about the language. And then we gave them 3 programming tasks in which we did not answer their technical questions. We only gave them a compiler, not a runtime environment, because our focus was on how the language would rule out bugs at compile time. We allocated 4 hours per participant, and we compensated our participants with a $75 gift card. So here's how the tutorial looked. In part, there was a document, and then there was an instrument that stepped through the document and gave them some practice, writing some small Obsidian programs or Solidity programs if they were assigned to that condition. You can see it took people roughly an hour and a half to complete the tutorial. There's a fairly large standard deviation. There's no significant difference between these two because the standard deviation is so large. Then in terms of tasks, we were interested in tasks that reflected use cases that the blockchain community would be interested in. We also wanted to choose a selection of tasks that had a range of different difficulties so that both novices and experts would be able to get something accomplished in the tasks. And then we wanted to see whether Solidity participants would accidentally lose assets and whether Obsidian participants would be able to accomplish the tasks that we gave them. We also wanted to know whether Obsidian participants would be able to use ownership in order to express a security constraint, and if so, whether doing so would be faster than writing that code dynamically. And then we were interested in how the two languages would compare in an open-ended kind of programming context. And today I'm going to focus on the first 2 tasks. In the first task, which we called auction, people were asked to complete code for an auction implementation. The thing that's special about this kind of auction is that when a participant places a bid, they're required to pay upfront And then when their bid is superseded by a larger bid, they get a refund. So we record the maximum bidder and the maximum bid amount. We also, due to a security convention on the Ethereum platform, we use this pending returns map, which records all the money that we owe to people whose refunds we have processed. This implements what's called the withdrawal pattern. And then we were interested in whether Solidity participants lose assets and whether Obsidian participants would achieve their programming goals. So here's the bid function that we gave them as part of this task. And you can see there are these two to-dos here. So in the case where, at the top, where there are no bids taken yet, this is pretty straightforward. We provided them that code. But in the case where this is the second or later bid, we have to see whether the new bid is large enough. And if so, we need to record their new bid. Otherwise, we need to return the bid to the bidder because they didn't bid a large enough amount for their bid to be accepted. So here's the code that one of our participants wrote. You can see that they recorded the new bid and they transferred money back to the bidder in the second to-do. Unfortunately, this shows two bugs because in the first section they forgot to issue a refund to the prior max bidder, and in the second section they neglected to use the withdrawal pattern that we told them they needed to use for security reasons. So you can see almost everybody in both conditions thought that they were done by the end of the 30 minutes that we gave them. This difference would be significant at the 0.09 level. But only 2 of the Solidity participants were able to complete the task correctly, whereas 6 of the Obsidian participants were able to do so. You can see that 2 of those who finished correctly lost assets. In the Obsidian condition, which I'm talking about, the error message that people got would look like the following one at the bottom. Variable max bid is an owning reference to an asset, so it cannot be overwritten. So this served as a reminder to people to avoid overwriting assets. Now, in terms of failures, we saw among the Solidity participants, 4 of them overrode the prior refund and 3 of them forgot the refund entirely. In the first case, people wrote code like this. They recorded the amount that a bidder was owed. Unfortunately, this assignment may overwrite any prior refund, so they should have written plus equals. They instead wrote equals here. In a prescription task, we were interested in enforcing this requirement that a prescription is only deposited once in any pharmacy, right? You can't take a prescription and deposit it in multiple pharmacies. So our solution here is to transfer ownership to the pharmacy. We were hoping that people would figure this out, so we gave them code in which you could deposit a shared prescription. We were hoping that people would figure out that if you transferred ownership at deposit time, that would solve the problem. On the other hand, in Solidity has no concept of ownership, so people needed to implement a global state tracking mechanism. We give them 35 minutes for this task, and you can see among the Solidity participants, 6 of them tried to write a dynamic solution, but only 2 of them actually finished in the amount of time we gave them. It's a fairly complicated piece of code to write for that amount of time. On the other hand, all 6 of the Obsidian participants who figured out that they could write a static solution did succeed in doing that. And the time difference was not significant, which is maybe not too surprising considering that not everybody finished in the Solidity case. Now, in terms of threats to validity, this kind of has the standard threats to validity in an experiment like this. It was a lab study in a limited amount of time with students. Tasks were modeled after real-world examples, but it's hard to be sure that this is representative of all possible tasks that people will do in the real world. So what observations can we make from this study? Well, experiments with sophisticated type systems are indeed practical. You can run them in a lab, you can get interesting results, you can teach the features in a consistent way, and find that some of the participants were able to leverage the features effectively in a relatively short amount of time. In the third task, which I didn't have time to talk about, we found that people abused a feature called disown in order to add bugs to their program. So this showed some opportunities for improvement, either in the language or in the documentation. So some keys to success to people who are thinking about running these kinds of studies. It's really important to iteratively design and pilot your documentation and your tasks. It's really hard to know in advance what problems people are going to run into and what things in your documentation are going to be confusing. It's important to draw tasks from real-world contexts in order to maximize the external validity of your work. It's important to recruit appropriately. In our case, we recruited mostly from master's students, and so we were able to get people who had a significant amount of real-world programming experience. And it's really important to include practice and assessment in the tutorial. We found that when we didn't do this in a tutorial, we just asked people to read a document, people kind of skimmed it over and didn't really absorb the material. In conclusion, we hope that you too will consider evaluating your language design with a randomized controlled trial. It's a long road. It took us about 6 months to do this, but there's no other way to know whether your work benefits people beyond yourself in a quantitative kind of way. It's important and useful to build and test the associated materials like documentation along the way, and as a nice result, you get the documentation out, and also you can identify opportunities for improvement. So thank you very much for listening to my talk.